All right. Well, good morning, everyone. Happy Thursday, and welcome to today's webinar on choosing the right conductivity sensor for your application. My name is Tony Sandfoss. I'm the technology manager for M4 Knick, and I'm joined today by a member of our marketing team, Mr. Seth Robinson. Seth's going to be assisting me today. Just a few things before we get started, folks. Please, as we go along the next 30 to 40 minutes or so, if you have any question at any point, please go ahead and submit that through the Q&A segment on the Zoom webinar here. And we'll take some time at the end of today's webinar to address those questions. So I do also want to mention that today's webinar is being recorded and it will be provided to you after the fact as well. So with that said, we'll go ahead and kick it off. Again, the topic of today's webinar is focused around conductivity measurements and specifically choosing the right conductivity sensor for your application. So we'll take a look at the agenda here. What we're going to cover today specifically is the fundamentals of conductivity measurements. There are three main types of conductivity sensors that are utilized out there on the market. And those three types are 2-electrode sensors, 4-electrode sensors, and then what's referred to as inductive or often referred to as toroidal conductivity sensors. So we'll take a little bit of time and cover the fundamentals of those different technologies. And within that, we'll sprinkle in some real-life applications across multiple different industries that apply specifically to those type of technology and those type of electrodes. And then finally, we're going to talk about maximizing accuracy and efficiency of your conductivity measurements. And we're going to focus specifically on what's referred to as solution temperature compensation. This is something that we see often out there in the field that is overlooked, or maybe solution temp comp is applied but not applied properly. So we'll take some time this morning to cover solution temperature compensation, specifically what it is, when to utilize it, and the benefits of utilizing that feature. So yeah, with that said, we'll go ahead and kick it off specifically on conductivity. And as you all probably know, throughout many different industries, many different plants, I know we have folks on today's webinar from the chemical industry, the refining industry. I see some pulp and paper customers, and obviously water, wastewater, standard utilities. Conductivity is one of the top measurements made in the world throughout our different facilities. And simply put, conductivity is the ability of a solution to carry an electrical current, right? It's measuring ionic activity. It really doesn't care specifically what ions, is so long as those ions are conductive, right? So it's a non-specific measurement, but it's influenced heavily by different ions, different species. And of course, it's a fundamental measurement of water purity. Whether you're operating a power plant or you have heat exchangers, we'll talk a little bit more about those in a specific application in a little bit, but water purity and specifically corrosion purposes, right? So, when we look at different corrosive environments, conductivity is often applied for monitoring corrosive properties within your plant. So, and the other thing to point out, we'll touch base on it, is conductivity is the basis for a lot of different other measurement parameters that are made within your facilities. Whether those are concentration measurements, we'll talk about specifically the M4 Knick technology and how you can utilize conductivity to make concentration measurements. We'll talk about how you can use this technology to make resistivity measurements. Maybe you're making those measurements in your facility. Those of you that are working in a semiconductor facility probably know a lot about resistivity measurements. TDS, total dissolved solids, salinity, all based off the principle of conductivity measurement. So that's also something that's often overlooked simple conductivity electrodes are used for a number of different measurement parameters out there. So just moving forward here, conductivity measurement, folks, it's electrical, right? So when we talk specifically, this diagram on this slide represents a 2-electrode conductivity sensor. And when those 2 electrodes are immersed into a liquid and we apply a voltage to them, a charge occurs and current flows in between those 2 electrodes. And that's proportional to really the conductance of the solution that we're measuring. So the positive cation ions move toward the negative electrode, and the negative anions move towards the positive electrode. We have this current flow that takes place based off the conductance of the liquid itself between those 2 electrodes. So we're applying a DC voltage to those electrodes. They're immersed into the process, and we get a current flow based off the conductivity of the solution that we're immersed into. So specifically, what is conductive, right? And again, we talked about different minerals, different species, particularly salts, right, in different solutions. And what we're showing here is an example of what are some known very strong electrolytes that are used throughout our facilities. Things like hydrochloric acid, sodium hydroxide. Those are considered strong electrolytes, strong carriers of conductance because they carry a high conductivity value. Known weak electrolytes, probably the most common is certain acids, certain solutions such as ammonia, and very specifically ultrapure water. Ultrapure water is a very, very weak electrolyte, and most folks should be familiar with ultrapure water not carrying a high conductivity. In fact, it's a very low conductivity, or simply put, high resistivity. So again, throughout our plants, that's why we monitor conductivity in ultrapure water, because that water is used often to generate steam, to turn a turbine. Obviously, salt mineral content in that water leads to corrosion, things of that nature. For those of us in the pharmaceutical industry, ultrapure water is used for water for injection. We mentioned semiconductor industry. It's used for polishing or cleaning. Whereas if we have mineral content within our cleaning water, our polishing water, that's going to impact, say, the circuitry on the wafers that we're producing. So again, disassociation of minerals and water, different minerals, different solutions can either be strong electrolytes or weak electrolytes. And the basis of the sensor technology that's out there on the market is designed specifically for measuring in these strong electrolytes or these weak electrolytes. So if we break it down, moving on here to specifically what is conductivity, and really the basis of it, if you're an electrical engineer, if you know anything about electricity, the basis of it is revolved around Ohm's law, right? So Ohm's law, where we calculate based off voltage and currents, we calculate resistance. Conductivity or conductance is the inverse of resistance. Hence, as I was stating earlier, these conductivity electrodes that we'll show you throughout today's webinar are often used for measuring resistivity. And the electronics that we have in the M4 Knick product portfolio allow you to display in resistivity and output to your control system in resistivity, because it's simply the reciprocal of conductance. So, however, though, conductance is not conductivity. It is not solely the conductivity measurement that we're looking for just yet. It's a key component of it. We're pulling conductance, but to calculate conductivity, we have one more variable that comes into play, and that variable specifically is the cell constant. So if you look at this particular slide here, we're showing 2 electrodes, and on those 2 electrodes we have an A and a D, right? We have A for the surface area, and D for the distance between those two electrodes. And what that is referring to, that obviously is the geometric makeup of those electrodes. And within the industry, we refer to that as the cell constant, right? So the cell constant is specific to the conductivity sensor that you're utilizing. Different conductivity sensors carry different cell constants, but simply put, the cell constant is the geometric makeup of the electrode. And that's the last piece of the equation, if you will, when calculating conductivity. We have conductance, right? Now we know the geometric makeup of our conductors, right? Our electrodes, and we can now calculate conductivity measurement. So again, that's simply put what goes into making these measurements. Let's take a little bit of time here and talk about the different electrodes or different sensors that are used out there in the industry, and more importantly, which one's best for certain applications. So specifically, the unit of measurement when we talk about conductivity is the Siemens. And again, when you often are looking at conductivity measurements in your application, you'll typically see in the range of either microsiemens or millisiemens per centimeter. Now that per centimeter is referring to the cell constant of the electrode. But what we're talking about as far as a unit of measurement is in the Siemens range. And again, the vast majority of these industrial measurements are made in either the microsiemen, very low conductivity, or millisiemens range. And you can see some typical values here, and what those refer to. Obviously, 1,000,000 microsiemens equals 1,000 millisiemens there. But it's important to note, and this is often how you'll see throughout your plants, the different conductivity values displayed on your pieces of measurement equipment. So again, let's talk about specifically the three types of conductivity sensors that are utilized in industrial applications. So if we move forward here, Seth, if you don't mind, I want to talk a little bit about two electrode sensors and their cell constant, right? So this diagram shows a few different two electrode sensors, the top two being coaxial style sensors. And the coaxial style sensor on the far right, the SE605 and SE604, and of course the SE625, have very small cell constants. And a small cell constant typically consists of a large surface area, but a short distance in between those two electrodes. And small cell constants are most commonly used for tight, small measurement ranges, right? So low conductivity applications. The three sensors that you see there, the coaxial style, the SE625, 604, and 605, are range from 0 to 1,000 microsiemens. So low conductivity applications is where we often utilize coaxial style two electrode sensors. Now, the two sensors that you see on the left, the SE615 and the SE630, these are also two electrode sensors. And most commonly, a good rule of thumb is around 20 to 30 millisiemens is really the max recommended measurement range for a two electrode sensor. We'll take an opportunity and we'll show the camera here. We actually have our SE615 two electrode conductivity sensor here. Again, this particular sensor, as shown on the last slide, ranged up to 20 millisiemens. The benefit of this style sensor, as you can see here, is that it is very compact. It's 12 millimeters in diameter, available in 120 millimeter length, right? We can also utilize a 225 millimeter length for use in standard industrial style holders, whether that's a simple static holder or a retractable holder, which would allow you to isolate your conductivity electrode from your process, pull it out of the process for cleaning purposes. This fit and form 12 millimeter diameter by 120 or 225 millimeter length lends very well to that design and to that application. So, specifically with these types of electrodes, we'll just move forward here. When you're looking at two electrode sensors, and again, specifically to that max measurement range, that 20 millisiemens measurement range, the reason we have additional electrodes in our portfolio really revolves around this phenomenon called polarization that takes place, again, at that higher range of a two electrode sensor. And what happens with polarization is that you have the ions start to collect or polarize at one of the electrodes of your two electrode sensor. And this can lead to inaccurate readings. So we recommend at M4 Knick, when you get above that 20 millisiemens range, we start looking at different types of sensors. So just want to note that, and we'll talk about the 4 electrode sensor here in a few slides. But this phenomenon of polarization is why most manufacturers, including us, cap the measurement range for a 2 electrode sensor at around 20 millisiemens per centimeter. When we talk about applications specific for 2 electrode sensors, probably all of you on today's webinar have cooling towers within your facility. Cooling tower monitoring is a very important measurement, right? Because we want to monitor performance, and obviously high conductivity inside cooling water indicates a high concentration of the dissolved solids. That can lead to scaling, corrosion, right? Fouling within the piping system. So oftentimes we utilize 2 electrode sensors such as our SE615 that I just showed. Even our SE630 can be utilized in these cooling tower applications. And the particular photo that you see on the screen here, this installation is utilizing that SE615 sensor, but in what we refer to as a flow cell housing. So we're bringing a sample off the cooling tower from the cooling water into the bottom portion of this pot, this flow cell. And the nice thing about this flow cell is it can house other analytical measurement sensors. And oftentimes for cooling water, we're monitoring pH, we're monitoring ORP. So again, that fit and form of that 2 electrode SE615 plays perfect here because you can house all of these in one sample flow cell, such as our ARF series here, the ARF 215 in the photo. So cooling towers, very, very popular application for 2 electrode sensors. The next one, referred to it a little bit earlier, but coaxial style 2 electrode sensors play very, very well towards those low conductivity applications. This is specific to the semiconductor industry. You could see the transmitter display there is actually in resistivity, mega ohms. And ultrapure water operates again in the nanosiemens range of conductivity, but in the mega ohms for resistivity, 18.2 is pure ultrapure water. And our electronics have the ability again to display resistivity values and output that to your control system as well. So the SE625 that you see here, we'll switch, we'll actually show it on camera here. This is a compact 3/4 inch NPT coaxial style 2 electrode sensor. It utilizes titanium electrodes. And again, the nice thing here is that it's very compact. It can fit into small flow cells. And the benefit, if you're familiar with the Knick technology MemoSense, is this is a digital sensor, right? So there's an analog to digital conversion that takes place with the MemoSense technology, and we have an inductive connection here on the head of the sensor. So this is our SE625, ranged from 0 to 1,000 microsiemens, ultra pure water applications, very compact installations. Great sensor, whether it be for UPW and semiconductor industry, or also pharmaceutical industry, RO, reverse osmosis measurements, things of that nature. Another very common application in industrial plants, and again, this can be whether it's in a refinery or a chemical plant. Oftentimes, many of you are utilizing heat exchangers, right, to cool a hot process. And those heat exchangers are typically made of an alloy, and corrosion, of course, can occur. Conductivity is a great technology to monitor for corrosion that may be taking place in a heat exchanger. And we refer to that type of application as a breakthrough application, where we can monitor the conductivity on the inlet side and monitor the conductivity on the outlet side. And they really should be close to equal, right? If they are not, and we have a change in conductivity on the outlet side, well, we know then we can assume that we have some sort of breakthrough due to corrosion occurring within that heat exchanger. This is a very common application that we make all the time. Again, the MemoSense technology with the Stratus transmitter that you see here in the image leads really well for fast indication of breakthrough within that heat exchanger that can lead to an alarm and, of course, action within your plant. And then lastly, as far as applications go, again, another high purity conductivity application. For those of you that are within power plants, or maybe you have utility side, you have a boiler within your plant, you're probably familiar with what is called CAT conductivity or Cashion conductivity. So specifically, when we look at conductivity for generating conductivity of makeup water for generating steam, we have what is referred to as specific conductivity, which is the raw conductivity made before a Cashion resin column that you see on the image here on the right. And then after that Cashion resin column, we'd utilize another conductivity sensor. Again, the SE625 lends really well to this application for making a CAT conductivity measurement. And really what we're doing is we're removing the alkalizing agents. Most commonly, that's ammonia that's used, that increases the conductivity value, and we're stripping that out via the resin column here. So as you can see on the measured values, very low conductivity. We're talking specific conductivity values in the single-digit microsiemens per centimeter range, down to sub-zero there, below 1 on the CAT side. So again, solutions there for high purity conductivity measurement specific to power generation and steam generation. So again, talking about why do we have different conductivity sensors, within our portfolio, or why do we utilize different conductivity sensors out there on the market? And when we get to that 20 to 30 millisiemen range and that phenomenon of polarization occurs, that's really when it's best to look at technology like 4-electrode technology or even inductive technology that we'll talk about in a bit, because you have the ability to eliminate polarization and achieve a much larger measurement range. And the way this works, we simply implement another pair of electrodes. We have a constant current that is applied to the two current or the outer electrodes, if you will. And then we have a voltage drop across the inner voltage electrodes, and that's measured specifically to the conductance of the fluid that we're in. Obviously, we're still utilizing Ohm's law, but the benefit here is that with high impedance amplifiers, right, there's no current flow in the voltage measurement loop that could lead to or occur with that polarization effect. So we eliminate polarization and we can go much larger on the measurement range here. So we'll switch to the next slide and show specifically the M4 Knick 4-electrode conductivity sensors. But the thing you'll note is how high up in the millisiemen range these sensors go to. On the left, we have our K25. Again, we'll show here in a second on the camera. You see the 12 millimeter diameter. The benefit there is for fitting into standard types of holders. But on the right, we've got our SE600 and SE603. very high temperature range, up to 410 degrees Fahrenheit, and up to 600 millisiemens per centimeter on the measurement range there. So applications that have heavy buildup, aggressive chemical applications with high conductivity values for electrode sensors are optimal here. I'll just switch the camera view here and show, again, this is the K25 4 electrode conductivity sensor. Just as with the SE615, we see 12 millimeter diameter, available in 120 millimeter length or up to 220 millimeter length to be able to install it into retractable holders. This particular sensor has a peak body, a robust peak body with graphite electrodes, 4 graphite electrodes on the face of this particular sensor. And if we go to the application slide here, you'll see that this lends really well in aggressive applications that are often found in industries such as pulp and paper. The image that you see here, this is a pulp washing application, operating range, in the 70 millisiemens per centimeter area, around 200 degrees Fahrenheit. So a hot application. And for those of you familiar with pulp and paper mills, you probably have some familiarity with liquor applications and how aggressive they can be on sensing technology. 4 electrode sensors such as this can be installed in a retractable holder. You see the image there of the sensor installed in that stainless steel tube. That's actually being inserted through a full port ball valve into the main wash line in this particular paper mill. So again, 4 electrode sensors, high conductivity value, often a high temperature range, eliminate polarization impact, very good for aggressive, rugged applications. And then third, and finally, the last technology that we're going to spend a little bit of time talking about is what is referred to as inductive conductivity, or often toroidal sensors. For those of you that have some familiarity with these are the donut style sensors, if you will, that you may have within your facility. And really what you have, it's an inductive coil, right? You have 2. You have a drive coil and a receive coil. So you see on the diagram there, a primary coil and a secondary coil. And what we're doing is we're inducing a current flow from the conductance of the solution when we apply power to those coils, right? Now the benefit here is by having these 2 coils, we can encapsulate them. So for those of you that are familiar with MemoSense technology, we have an inductive coupler on the head of the sensor. Well, this is inductive coils on the sensing element of this donut style or toroidal style conductivity. So again, aggressive chemicals, this suits very well. It's a non-contacting conductivity sensor. If you look at the M4 Knick product portfolio for inductive conductivity sensors, the SE655 and 656, the benefit here, you see the 655 is a peak-bodied sensor. So again, completely encapsulated in peak, heavy resistance there, great chemical compatibility. And even further, the SE656, that's a PFA encapsulated sensor. So again, aggressive chemicals, high measurement range. So you see up to 2,000 millisiemens per centimeter on the toroidal side of things. Moving over to the right side, we've got our SE670 and then specifically the SE680, another peak-bodied sensor, hygienic peak, very unique. I'm going to switch the camera here and actually show the SE680 sensor. We have this available again in FDA-approved peak material, completely encapsulated. But one of the very unique benefits of this model sensor is this feature right here, this nub on the end of this sensor that is also fully encapsulated in peak is actually the temperature detector. So if you think of this type of technology we showed on the previous slide, we've got 2 coils encapsulated in here. Of course, conductivity is temperature dependent measurement. So we must have an integrated temperature detector in these sensing elements. And often in toroidal or inductive conductivity sensors, that temperature element is embedded behind the coils. So it takes a little bit of time for the sensing element or the measurement to stabilize and come up to process conditions. With the SC680 and also with the SC670, we bring the temperature detector outside of those coils. So it's a much faster responding temperature detector here that leads to quicker uptime and stability on the measured value. So we'll show a couple applications here specific to use with the SC680. One of those specifically is concentration measurements. So concentration measurements lead really well for use with inductive conductivity sensors simply because we're typically measuring concentration of aggressive acids most often, or caustics. And that completely encapsulated sensor body lends well to chemical compatibility. As I already mentioned, the Knick series of transmitters, whether those are 2-wire transmitters or 4-wire transmitters, have concentration curves built into them. So you have the ability to display locally in percent concentration, but also output back to your control system in concentration as well. So this particular application is in steel production. Oftentimes on the pickling lines, we're measuring concentration of acid there, and conductivity is a great technology to use for measuring that concentration. Here's an example of sodium hydroxide concentration curve that you see. So these curves, how they look, they're specific based off conductivity and temperature. The gray area in the curve is specifically stating that concentration determination is not possible here. But if you look in the manuals of any of the Knick transmitters, you'll find a number of different concentration curves. HCl, sodium chloride salts, oleum. We have these built into our technology to be able to give you a direct concentration display and output to your control system. Another great application, moving to a completely different industry, this being food and beverage industry, for inductive conductivity sensors, and you see the image of the 680 here, is CIP monitoring. CIP, or clean in place monitoring and control, specifically in the beverage industry or in the dairy industry. When we're cleaning the lines, the filling lines, if you will, or any lines that are carrying liquids, and we want to run a CIP, a clean in place procedure, that cleaning agent, we often want to determine the concentration of the cleaning agent being used to ensure, one, we get adequate cleaning, and two, we're not overusing, which leads to higher spending on the cleaning agent itself. So concentration measurement with technology such as inductive conductivity or toroidal sensor is often utilized. And then further, to add to that, once we're done with the CIP cycle and we're running that cleaning agent through our lines, most commonly we're going to run a rinse water through to make sure any residue is cleaned out of those lines. And conductivity can be utilized, low conductivity measurement, such as with the coaxial style 2 electrode, you see the SC605 here, can be utilized to measure the rinse water after the CIP cycle has occurred. So very common application, CIP monitoring, utilizing both an inductive toroidal conductivity sensor, the SC680, and then a 2 electrode sensor in the SC605. So quickly here, again, we covered steel, we covered food and beverage, we covered semiconductor. These are just a few of the applications that can be made utilizing conductivity sensors throughout different industries. Pharmaceutical, Wi-Fi water for injection. It's very, very important to monitor the conductivity. We want that to be low conductivity. Breweries, power generation, boiler steam generation, a number of different applications utilizing conductivity measurements. And then lastly, on the next slide, you see aggressive industries, right? So the chemical industry, oil and gas, pulp and paper. Seth, if you don't mind switching the slide there. So these industries, we have concentration measurements. We've got, sewer measurements, outfall measurements, monitoring conductivity. Again, a number of different applications specific to the three types of conductivity measurements. So lastly here, within the next 10 minutes or so, I want to take a little bit of time to talk about accuracy and efficiency around temperature. Again, temperature has a heavy influence on conductivity. As conductivity changes, right, the ion activity, the solution is changing conductivity. So the mobility of those ions and the dissociation is heavily dependent on temperature. And oftentimes, what we're doing within our facilities is we're making online conductivity measurements and we're comparing them to something, right? We're comparing them to grab samples that are taken at the point of measurement, then transported often to our lab. At that point, the lab takes a measurement, verifies what that conductivity value is, and compares it to the online reading. Well, what happens between that time that the grab sample is taken and then brought to the lab, right? Temperature has changed. It's often cooled. So most commonly what you'll see is a calculation or a correction of the online conductivity value to a reference temperature, that being the temperature that the grab sample is taken in the laboratory. Typically 25 C, 77 degrees Fahrenheit. And what solution temperature compensation does is it allows you to apply a coefficient based off the process that you're monitoring into your transmitter with a set reference temperature to compensate that online value to the reference temperature value, right? So the lab value, because obviously if we're making a conductivity measurement online, talking raw conductivity, it's say 200 degrees Fahrenheit. We take that grab sample, we bring it to our lab, it's cooled down to say 77 degrees Fahrenheit, the conductivity is changed. And what we utilize in the Knick technology is what's referred to as solution temperature compensation. And we have a number of different capabilities of inputting that coefficient, if you will, into the electronics. Most often that's done via a linear coefficient. So we plug one coefficient value in and it's across a linear line. But tables can also be built because, again, most solutions are not linear, right? This actually shows that salts up to 5% concentration have a significant difference as temperature increases. Natural waters, ultrapure water, for instance, has a major impact or influence of the change in temperature on it. So solution temperature compensation, again, is something that should be looked at within your facilities, specifically if you're referring those or referencing those to your grab samples and then your lab values. In the previous slide, I'm going to ask Seth just to back up once to the formula there. The previous slide shows the most common formula that's utilized to develop these coefficients. And again, all solutions have their own dependency on temperature and conductivity value. What this formula shows here is creating that coefficient. And what we typically recommend to folks is take a grab sample, right? Know your raw conductivity at your online temperature. Take a grab sample. Utilize something like a portable meter, like the Portavo from Knick, and start your data logger. The Portavo has an integrated data logger. You can take that grab sample, take a conductivity reading at process temp, start your data logger, let that sample cool to the reference temperature, and now you can take those values, your conductivity at your online temp and your conductivity at your reference temp, plug them into this equation and calculate your coefficient that would be installed or inputted, if you will, into your electronics. And what that's always going to do is compensate that online conductivity value to the reference temperature that you're utilizing when you take your conductivity value in the lab. So again, important to note, the Knick technology has this built into it. You can activate it, you can set it as linear, you can develop your own table, if you will, so you can have coefficient per 5-degree increments to get a much more accurate, temperature corrected conductivity value. So again, I hope everybody found this beneficial. I just wanted to make sure that people understand the differences in the 3 technology, 2 electrode technology, 4 electrode technology, and then inductive or toroidal technology, and where they apply best to applications within your facility. It's very important, obviously, that you select the right sensor. If you're in an application that has very low conductivity, of course, an inductive sensor or a 4-electrode sensor can cover that range, but you might not see the resolution that we would expect to get out of something like a coaxial 2-electrode sensor. If you have a large measurement range with an aggressive chemical, right, you want to look at something like an inductive sensor because it's non-contacting. Those electrodes are not going to be impacted by chemical corrosion and things of that nature. So very important to select the right conductivity sensor based off your application and the characteristics of that application. And then further, very important to take temperature into account and specifically understand what solution temperature compensation is and how it can benefit you. So with that said, this is just a reminder, if you're not already, please follow us, M4 Knick, at LinkedIn. We have Instagram, are on YouTube as well with a number of videos. And if you have any questions further after today's webinar, there's my email address. I'm the technology manager for M4 Knick. Would be happy to answer any questions or discuss any applications with you. So we're going to take the last few minutes here to see if any questions came in before we sign off for today. So just want to thank everybody for attending. So we received one question in specific around online resources for conductivity ranges and more specifically for HCl, hydrochloric acid ranges. We do have some published literature that's in specifically the transmitter technology. So those concentration curves again show the conductivity and concentration ranges for HCl specifically. Oftentimes HCl, as we increase the concentration of HCl, we'll look at a non-contacting type sensor like a toroidal or inductive conductivity sensor. It truly depends just simply on how high of a concentration of HCl you're using. But non-contacting encapsulated technology like the toroidal sensors is often utilized. So we received another question regarding professional development hours. For today's webinar, there's nothing included as far as professional development hours that will come from M4 Knick. But I encourage you specifically to check out our upcoming events. We have an process analyzer technology forum coming up in a few weeks in the Houston area where professional development hours will be included. So be sure to follow us, check out our events. We have some of those coming up where development hours can be accumulated. All right, with that, last call for questions. Again, the contact information is on the screen there. So if anything comes up after today's webinar, please feel free to reach out to us. And again, lastly, just want to appreciate everybody's time. And you will be receiving a link in the near future to a recording of today's webinar. So thanks everybody and have a great rest of your week.